In this presentation, we have to talk about divergence of function in terms of orthogonal curvilinear coordinates. You know the term divergence. Divergence of a vector points out the amount of flux coming out of a system per unit volume. Therefore, div of a vector is equal to v dot ds, flux coming out of the system per unit volume. D tau is the volume. Now read out this. The divergence of a vector function v has been defined as the limiting value of the surface integral of vector v over the surface bounding the volume element d tau per unit volume as the volume of the element tends to 0. In general, the divergence of a vector points out outward flux per unit volume. Here the volume element d tau is equal to h1, h2, h3, dq1, dq2, dq3. Consider this volume element q1, q2, q3 are the three curvilinear coordinates. In this volume element, in total 6 faces are present. Now consider the faces 1 and 2, opposite faces. This is h3 dq3, this surface. Then the side is h2 dq2. Then the height is h1 dq1. If you want to calculate the volume of this surface, you should multiply all these three, h1, h2, h3 into dq1, dq2, dq3. If you want to find out the area, just multiply h3 dq3 into h2 dq2. This side into this side. Say this is h3 dq3, this is h2 dq2. Multiply these two for area. For volume, we have to multiply these three. Now, as shown in the figure, consider a volume element. In order to find div of the vector v, we have to compute the surface integral of vector v over the surface of elementary volume d tau, that is v dot ds. First, consider the surfaces marked 1 and 2. See, these two, 1 and 2. In total, 6 faces are present. Consider these two faces, 1 and 2. First, consider surfaces marked 1 and 2. Assume that the vector v has average values v1 and v1 plus del v1 over the surfaces 1 and 2. The value of the vector at the surface 1 is v1. The value of the vector at the surface 2 is v1 plus del v1. Hence, the contribution of these surfaces towards the surface integral is v1 plus del v1 into this is the value of vector at this point into then ds value h3 dq3 into h2 dq2, h3 dq3 into h2 dq2. This is surface area, this side into this side, minus of v1 into h3 dq3 h2 dq2. Now see this. Assume that vector v has the average values v1 and v1 plus del v1 over the surfaces 1 and 2. The value of the vector at the surface 1 is v1. The value of the vector at the surface 2 is V1 plus del V1. Therefore, the difference is V1 plus del V1 minus V1. Now, the contribution to the surface integral is vector dot ds. Vector value is V1 plus del V1 at this point 2, and the surface area is this side into this side, that is surface area. H3 dq3 H2 dq2 minus, then the vector value at this point is V1 into surface area H3 dq3 H2 dq2. The difference in vector is the value of vector at the point 2 minus the value of vector at the point 1, that is V1 plus delta V1 minus V1. This is the difference in value of the vector, but we are calculating V dot ds. The surface area is this side into this side, side into side. Now this is equal to V1 into this quantity minus V1 into this quantity. This is V1 H3 dq3 H2 dq2 plus delta V1 H3 dq3 H2 dq2 minus V1 H3 dq3 H2 dq2. This is equal to delta V H2 H3 then dq2 dq3. The contribution of these surfaces towards the surface integral is this much, but delta V, here this is V1 because we have specific V1. Delta V1 equal to dou V1 divided by dou Q1 into dQ1. Substitute this value in the above. We can write dou V1 divided by dou Q1 H2 H3 into dQ1 dQ2 dQ3. Now multiply the above equation by H1 H2 H3 and divide the same by H1 H2 H3, which is equal to 1 by H1 H2 H3 dou V1 by dou Q1 H2 into H3, then H1 H2 H3 dQ1 dQ2 dQ3. Multiply by H1 H2 H3, divide with the help of H1 H2 H3. There is no change in the value. We know that the value of H1 H2 H3 into dQ1, this is our d tau. Already we have pointed out the volume element d tau equal to H1 H2 H3 dQ1 dQ2 dQ3. Therefore, the above equation is modified as one by H1 H2 H3 into dou V1 by dou Q1 H2 H3 into d tau. This is further modified as 1 by H1 H2 H3 dou by dou Q1 of V1 H2 H3 into d tau. Now we should go for the contribution rendered by others. Similarly, we can find the contribution of other parts of opposite faces towards the surface integral. So here we have taken only these two faces 1 and 2. In total 6 faces are present. This is one pair. Another 2 pairs are present. Similarly, we can find the contribution of other pairs of opposite surfaces towards surface integral. Adding all these contributions, we get. Now we have to find the value of v dot ds. That is equal to, go through the first contribution. First contribution is dou by dou q1 of v1 h2 h3. One by h1 h2 h3 into dou by dou q1 of v1 h2 h3. In the same manner, you can write dou by dou q2 of v2 into h1 h3 plus dou by dou q3 of v3 h1 h2. Entire is multiplied by theta. This is the value of v dot ds. We have arrived at the relation 1 by h1 h2 h3 dou by dou q1 of v1 h2 h3 d tau. This is due to the contribution by the 1 and 2 phases. Then these two are contribution rendered by other two pairs. Now IV equal to v dot ds divided by d tau. Here the limit d tau tends to 0. This is the value of di v. Then we can write 1 by h1 h2 h3 into dou by dou q1 of v1 h2 h3 plus dou by dou q2 of v2 h1 h3 plus dou by dou q3 of v3 h1 h2. This is the value of di v. Di v in orthogonal curvilinear coordinates. If you want to know the value of Laplacian operator, put v equal to grade pi. We know the value of gradient operator. Gradient operator is equal to E1 1 by H1 dou by dou Q1 plus E2 cap 1 by H2 dou by dou Q2 plus E3 cap 1 by H3 into dou by dou Q3. This is the value of gradient operator in orthogonal curvilinear coordinates. Now, from the above relation, see this is del dot. Instead of v, we have to put del pi. That is equal to 1 by h1, h2, h3 dou by dou q1, h2, h3 divided by h1 into dou pi by dou q1 plus dou by dou q2 of h1 h3 by h2 into dou pi by dou q2. Here dou by dou q2, this v2 is replaced by grade pi. This is the gradient operator value. That is h2 e2 cap 1 by h2 dou by dou q2. Therefore, dou by dou q2 of v2 h1 h3 by h2 into dou by dou q2 of pi. That is dou pi by dou q2 plus dou by dou q3 of h1 h2 by h3 into dou pi by dou q3. So this is dou by dou q3. Yes, it is correct. We should provide some modification. Dou by dou q3 of h1 h2 h1 h2. Here v3 is replaced by grade pi. That means this term h1 h2 by h3 to dou pi by dou q3. Now the value of del square is equal to, see here, del dot v. This is div of a vector. If you replace v by gradient of a scalar function grade pi, then the gradient operator in spherical polar coordinate, in orthogonal curvilinear coordinates is e1 cap 1 by h1 dou by dou q1 plus e2 cap 1 by h2 dou by dou q2 e3 cap 1 by h3 into dou by dou q3. This is the value in orthogonal curvilinear coordinates. Curvilinear coordinates. The grade operator in orthogonal curvilinear coordinates is this much. Now del dot v is this much. Keep this 1 by h1 h2 h3 as such. Put this dou by dou q1 as such. Then h2 h3. This v1 is replaced by grade pi. Here we have to write grade pi 1. Grade pi 1 is e1 cap 1 by h1 into dou by dou q1. E1 is a unit vector. If you take the dot product, I dot I is 1. Therefore, this term is unity. Dou by dou q1 h2 h3 divided by h1. This dou by dou q1 is operating on the function pi. In this way, we may get all other terms. Now, the value of del square is 1 divided by h1 h2 h3 dou by dou q1 of h2 h3 by h1 into dou by dou q1 plus dou by dou q2 of h1 h3 h2 dou by dou q2 plus dou by dou q3 of h1 h2 by h3 into dou by dou q3. This is the value of Laplacian operator. This Laplacian operator in orthogonal curvilinear coordinates. Laplacian operator in orthogonal curvilinear coordinates. Laplacian operator in orthogonal curvilinear coordinates. This is divergence in orthogonal curvilinear coordinates. This is divergence in orthogonal curvilinear coordinates. This is gradient in orthogonal coordinate.